Test, test. Okay. It said my mic wasn't working, but it was. Weird. Okay. Let's see here. Oh, no way, it's upside down. I tested this and it was fine. Oh, that's a scam. Okay, I guess I'll just plug it in backwards. It's gonna get real trippy. Oh, wait, no, I'm just blind. It was fine. I was looking at the wrong thing. Okay, let's fix that. That's better. See, it was backwards because I double page my book and I go it once the right way around and then once backwards because flipping pages is hard. Okay, there we go. This is still like 10 minutes early, by the way. So feel free to skip ahead in the recording. I don't think anyone's going to join for a while. This is just me setting things up. That's weird. I can drag this and it actually interferes. That's funny. Hmm. And so the meeting officially begins with a sum total of 0 people. All right. Well, I guess I'll do my best impression of a teacher who is lecturing to thin air. Yeah, why not? I know at least one of you will enjoy this recording, maybe to have as something to watch back to, or just to remember. Okay. Well, I know at least one of you was having a bit of troubles with when to use what types of equations when it comes to probability. There's all those types of probabilities when it comes to discrete. You've got both discrete and you've got the subset of discrete, which is binomial. And so in this lesson, we'll have a look at what we're actually doing in those situations and when we should use what. So discrete probability is all about this idea that quantities can only occur in very specific values, right? You can either have, if you imagine rolling a dice, right, you can only roll 1 to 6, right? You can't roll half of a one, right? You can't roll a half on a six-sided die. That's just not going to happen unless you have very special dice. That's what discrete is all about. You have very specific outcomes and only those outcomes. However, when it comes to continuous, which most of you wouldn't have looked at, considering continuous is a year 12 thing. When it comes to continuous, the difference there is that all the outcomes there can be arbitrarily accurate. And what that means is just if you imagine like measuring the length of, let's say, measuring the length of an object, and that object could be 1 meter long if your ruler was only so accurate. But if you looked a bit closer, you would notice there's a few more notches on that ruler, and you might say, well, okay, it's actually closer to 1.02 meters. Sure. But if you have an even more accurate measurement tool, you might get 1.02373 and so on and so forth. The accuracy that you have is purely dictated by the measurement tool that you have. It is continuous. There is no exact value when it comes to continuous, it just is. And so we only truncate decimal place at usually 4 decimal places is where math methods tends to cap out. You'll never really see anything beyond that. That's what continuous is all about. We don't worry about that for now. We just look at discrete. So discrete probabilities are usually described to you in the context of discrete probability tables or probability distribution tables, as I've titled it there. What these do is they show you all the possible outcomes of a discrete probability scenario, and they tell you the probabilities of each of those possible outcomes. So in this example that you're seeing here, the discrete random variable could only take the values 0, 1, 2, or 3. In the dice roll example, those numbers would be 1 to 6 instead. Those are just the outcomes of your scenario. One of the examples I went through literally about half an hour ago was the discrete random variable was the number of trees that had leaf damage. And it looked at a sample of 3 trees and it said, figure out the distribution of trees that are damaged. And so you think, well, okay, either no trees could be damaged, 1 tree, 2 tree, or 3 out of 3 trees could be damaged. Those are the outcomes of your experiment. As for how you calculate those, a little bit different. We'll look at how we actually do that in, well, 1 page down. But before that, it's worth considering what are the rules around probability tables. The first rule that you have to be aware of is that all probabilities in a table have to add up to 1. The reason why that's important is because all the probabilities have to add up. Well, the reason why that's the case is because a probability table tells you all the possible outcomes of your scenario, whatever that is. And so there's 2 possibilities that happen if your probabilities aren't adding up to 1. The first is that you calculated it wrong. And the second is that you haven't considered all the possible outcomes. Those are the only 2 possibilities because you must always have to add up all your probabilities to 1. What this actually said, what I should have been talking about, was the fact that all the probabilities must be between 0 and 1. And that's just a probability thing that happens in all probability, not just discrete. A probability of 0 means it's never going to happen. A probability of 1 means it's certain. And anything in between that is, well, a different likelihood. So all probabilities on the table between 0 and 1, they have to all add up to 1. And the last thing that's also important here is a lot of the times you don't need the entire table. So if you only wanted, for example, if you wanted to find the probability of x equals 1, x equals 2, and x equals 3 all combined, you don't necessarily have to do that. You can find the complement to that, which is find the probability of x equals 0 and then do 1 minus that. The reason why is because, well, everything has to add up to 1. So if you have this plus this plus this plus this all equals 1, all of these combine together to be their own little thing. And then 1 minus this must therefore give you this. That's how that works. And that's really helpful for a lot of circumstances. We'll see how that works. So, okay, one of the examples I have here, pretty typical one, just filling a jar. So we suppose that our jar contains 4 white and 6 black balls. 3 of them are drawn at random with replacement. And we're expressing that probability distribution on a table. Now, the term here with replacement, that tells you that when we're picking out these balls from a jar, it means that every time you pick it out, you just sort of note the color that you have and you put it back in, right? That's what the scenario is discussing. You pick it out, look at the color, put it back in. Do that 3 times over. Why that matters is because the probabilities from trial to trial don't change. And so you can use a probability, you can use a tree diagram for that if you want, but it's not super necessary anymore because now all you're looking for is um, if the probabilities are the same, then things done in sequence, they just multiply together. So you don't really have to think all that hard about it when the probabilities aren't changing. Tree diagrams are usually better off for with replacement, or without replacement rather, which we'll look at later. But okay, to start filling out the table, let's imagine we're trying to fill out x equals 0. Well, x equals 0 just means that you're only drawing black balls. The reason why is because the table is set up in the context of white balls. It said express the probability distribution of selecting a white ball. So for x equals 0, that means getting 0 white or therefore 3 black. So if we think about the probabilities of those events occurring, if there's 4 white and 6 black, you have a total of 10 balls. And the probability of any event occurring is just how many of those things do you have, or I guess how many things in the sample space have that attribute divided by the total sample space. So if we have 6 black balls and 10 total balls, then the probability of getting a black is going to be 6 out of 10. You can simplify that if you want, but you'll need to simplify it at the end anyway. So it's usually better off to, especially when it comes to having a lot of these like combining, like you can see them here. It's usually easiest to keep it unsimplified and then simplify at the end. But okay, if we only want black, well, we're just going to do black times black times black. The reason why it's multiplication is because it's in the sequence. And that's going to give you 27 out of 125. Or if you're doing decimals and you have a cas, then you would just do 0.216. Just makes it a bit shorter. And then for x equals 1, well, we have a bit of a weirder situation there. We've actually got 3 possible outcomes here. You don't necessarily have to count the number of outcomes. We'll look at that in a bit when it comes to binomial things. It's a bit of a sneak peek from later. You can use your counting methods knowledge to figure out these combinations beforehand. But okay, so for x equals 1, you're just going to have 1 white ball and 2 blacks. Now, those can be done in any order. That's why there's all these other outcomes. You could have white, then black, black. You could have white in the middle, or you could have white at the end. And so what we're going to do is calculate each of those options. Now, what you're going to see pretty quickly is that it doesn't actually matter what order you have. The only thing that actually matters there is the number of combinations. Because you can see here that having 4 out of 10, 6 out of 10, 6 out of 10, no different if you flip the order, because multiplication can be done in any order at once. So it doesn't actually matter what order you do them in. The only thing you care about is the number. So you would just do one of these and multiply it by 3 since you're doing it 3 times. X equals 2, same deal. You just figure out your combinations or you use your counting methods understanding and you calculate. This time it's 2 whites and 1 black. X equals 3, 3 whites. We've discussed what this looks like. It's just going to be the white times white times white. One thing you might want to do at the very end is make sure that your probabilities add up to 1. And so you just go through, add them all up together, equals 1. Nice, we've done it. You can also check and make sure that your probabilities aren't negative. That's very rare. I don't think I've ever seen anyone get a negative result for a probability. But there's always a first. Okay. Sometimes we're not necessarily looking for just the probability of one outcome. Sometimes we're looking for the probability of multiple outcomes, probability over an interval. In those cases, especially when it comes to, well, only when it comes to discrete, this is when we are adding all the probabilities in that interval. So if you wanted to find the probability that x is greater than or equal to 2 for this particular discrete probability table, then what you would do is you would add the results x equals 2 and x equals 3 together. So you might be given them immediately, like we were in this case, or you might have to solve them, in which case you would look at the previous methodology for that. Yeah, so you just add those 2 numbers together, and that's your outcome. That's not the only way that you can solve those. If you have probability x greater than or equal to 1, for example, um, let's suppose we didn't know what these other outcomes were, right? These are unknown. We know together that they equal zero point 0.7 because everything in this table has to add up to 1. So if this is zero point 0.3, then the rest of this needs to add up together to give zero point 0.7. So we know that. Um, and that's actually what we use because for probability x greater than or equal to 1, it would require us to do x equals 1 plus x equals 2 plus x equals 3. And so we use that idea of complement probabilities to figure out what this must have therefore been. I've never actually seen a question like this. I just thought it'd be nice to have a look. Usually you get a table that's full, or well, you get a table that's empty entirely, and it's up to you to fill it and then solve. So it would be much easier if you were to just solve the x equals 0 bit. Like if you imagine going through all these, these are pretty hefty calculations, right? Trying to do all of these. Um, Especially when the probabilities change from trial to trial, that can become even worse. So the least amount of effort that you can put into it, the better. But yeah, that's using complement probabilities. Makes life a lot easier. The last and probably most complicated bit of this type of area of study is when there's unknowns in the table. And we kind of had a look at that with the question marks here. This one's a little bit different though. You can see we've got like quadratics in there. We've got x or p squared terms in here. So the way that you find, well, the way that you solve these types of equations, if you're trying to solve for p in this situation, you're pretty much always going to rely on the fact that everything has to add up to 1. If everything has to add up to 1, that gives you an equation that you can solve. And so you're just going to grab each of these terms individually, add them all together, and set it equal to 1. From there, you're going to get some quadratic. At least in this case, it's a quadratic. You might have other crazier examples that could be circular functions, could be linear. Linear is more common, quadratic a bit less common, but it's worth understanding how to do quadratic because, well, if you can do quadratic, then you can do linear, definitely. You can solve this however you like. The way I've done it here is quadratic formula. Trying to factorize this would be a bit tough because you'd have to use a rational root theorem to get that p equals a fifth. That would be less than ideal. Maybe not necessarily. I could see a world in which you use like the factor theorem to factorize this. If you could find the factor x equals, what would that be? Yeah, the factor x plus 1. Then you could probably go ahead and do your polynomial division and solve it that way. Still not ideal. Probably quadratic formula is the best way to go about that. The last thing to consider here is that, well, we've got two outcomes. That's a bit weird. What we need to make sure is that the probabilities are between 0 and 1. We can't have any negatives in there. And so pretty much every time that negative is going to be invalid, right? We can't have a negative result there. But it's worth understanding a small distinction there. Just because P is negative doesn't necessarily mean the probability is negative. P, in all these circumstances, there is no P on its own, right? They're all attached to a coefficient. It's the product of the coefficient and the P value that actually makes a probability. So if you were to look at x equals 1 here, the probability is P squared. If P was negative 1, then negative 1 squared just makes 1. That's actually valid, right? That meets our criteria. The probabilities have to be between 0 and 1, and, well, it doesn't meet the other criteria, which is everything adding up to 1, which is another issue. But it just goes to show that just because you have a negative p value does not necessarily mean that the probability is negative. It does in the vast majority of cases, but I could imagine some separator question that tries to just sort of throw you off the case. But yeah, that's that. Conditional probability exists in every probability area of study, and the way you solve it is identical in every area of study. You always start by creating your conditional probability equation, which is just going to be the intersection of your two events divided by whatever the conditional is. In this case, it was literally told to you. In other cases, it might be worded. It might say find the probability that one tree has fallen given that less than three trees have fallen. If you think about the previous example I mentioned, right, that word given implies a conditional probability. When it comes to solving these, I usually focus on the numerator first. What you would do is would look at your intersection of those two events. And one of the things I recommend is drawing a number line if you can't immediately see what's going on there. You would just draw the two things. Okay, so I have x greater than or equal to 1. That looks like this. I have x less than 3. That looks like this. And so the intersection of those two events, well, that's just going to be where they're common, right? Where they overlap. And so if you were to write that as a specific interval, that would just be x is between 1 and 2 inclusive, which is what I've written down here. As for the rest of it, well, we can calculate all of these individually. X between 1 and 2, well, it's just going to be those two things added together. X less than 3, well, you could do all of these things added together, or you could do the complement idea, where you just do 1 minus this. That's purely a preference thing. I think a lot of people would prefer to just do 3 additions than a 1 subtraction. Subtraction tends to be on the harder side. But either way, when you simplify that fraction, you would get 10 out of 13, which you probably wouldn't have it as a decimal in this case. You'd probably want these as all fractions instead, just so you can make that math a bit nicer. Bit hard to have decimals over fractions. But okay, that's how we handle at least the key circumstances there. The other key thing to watch out for would be the binomial side of things. Let me grab that one up. So binomial is also discrete. It's very similar anyway. It's a subset you can think of as discrete. It's a special kind of discrete probability which meets these 3 criteria. So what you want to make sure of is that there's only 2 possibilities for your scenario, right? You either get a success or a fail. Your tree is either damaged or it's not. You either draw a black ball or a white ball, right? There's only 2 possibilities in our scenario. In fact, that's where the name came from. Binomial, binomial meaning 2, basically. If you think about the binary system, ones and zeros of a computer, it's, well, ones and zeros. It's 2 outcomes. The other criteria that you need to meet is independence and probabilities don't change from trial to trial. Now, these things here are a bit strange to try and identify because when you start thinking about these things intuitively, it tends to be the case that you can run into an issue where you start using real world logic to think about whether or not it would be independent or not. There was one example that we came across, well, that I've come across before, which is this one here. Right. In a large batch of eggs, 1 in 3 is found to be bad. What is the probability of whatever? Point being is this is our scenario. We have a large batch of eggs, 1 in 3 is found to be bad. Now, if you're thinking real world scenario, there's a decent case you could make to say, well, maybe that's not independent. If one of the eggs has gone bad, then maybe refrigeration has been bad, or maybe the entire batch was damaged, right? If you start thinking about the real world scenarios there, then there's a decent likelihood that you could give a decent argument to say that this isn't independent. Problem with that, if you have a look at the question, it doesn't give you any information to handle that if that was the case, right? If it was conditional, if it wasn't independent, then there's nothing you can really do about that. The only thing we know about this scenario is that 1 in 3 eggs are bad. So when it comes to identifying these 2 factors, these 2 criteria, it's less about looking for what the question says about it. Like there's no statement that'll tell you, well, sometimes there is a statement for independence, like here. But in most cases, it's less about looking for a statement that says that one of these things is true, and it's more about looking for statements that claim otherwise. So what I mean by things that claim otherwise would be like, let's find it, would be like this one here. So this one here is a situation where Each of the probabilities are conditional. They are based on what happened earlier. Definitely not independent. One of the statements here is if Delaney orders a coffee one day, then the probability of ordering a coffee on the next day is 0.5. Right, it's an if-then statement. Definitely not independent. Same thing here. Coffee on one day, the probability of coffee, well, not ordering coffee on one day, the probability of ordering coffee next day, 0.8. It's dependent on what happened earlier, right? It's when you have these tree diagrams that have different probabilities. So it's more about identifying, is this kind of language being used in the question, or is it this kind of language? And you'll kind of notice it just off the bat. These questions, they're short, they're sharp, there's not a whole lot going on there. These questions, they're a novel, right? You can see almost just from the size of the question what type of question it is. So that's how we identify binomial. It's usually by what it lacks rather than what is included in there. There's also some other key terms that you could have a look at. This idea of replaced, returned, with replacement, right? That sort of thing. The reason why that's important particularly is because um, binomial requires probabilities not to change from trial to trial. So if everything is replaced every time, like you pick out the ball, you put it back, then you just left it as is, as if you've done one additional trial. Doesn't matter what happened on the previous trial. Using words like independent, it might use the notation. That's a dead giveaway. It tells you it. These are also dead giveaways. And this idea of fair trials, fair just meaning 50-50, right? The classic example here is your coin toss, 50-50, and the fact that I tossed a head on the previous toss has nothing to do with the fact that I've tossed a head on the next toss. The advantage of identifying whether or not you have a binomial experiment is presented here, right? We can use the Bernoulli sequence in this situation. That's what I was sort of getting to when it came to this situation up the top here. When you use the Bernoulli sequence, you don't have to think about all the possible ways you could arrange this thing. You don't have to count them all out because it's handled here. It's handled by the NCR term, which from counting methods you would know is just um, the number of selections, right? How many ordered pairs can I create from my set that don't duplicate? Um, you've also got this P term in here. You can think of the P term as the probability of your particular outcome occurring. So if we look at that bad eggs example, if we're told 1 in 3 eggs are bad, well, that means your probability of success or probability of outcome is 1 out of 3. So the particular outcome for this binomial experiment is all written in terms of number of bad eggs that we have. The N is the number of trials, the number of times you repeat the experiment. Again, if we look at this example here, in a batch of 4 eggs, the batch is 4 eggs wide, and so the N, the number of trials that you have, is 4. For X, that's the number of outcomes, right? The number of outcomes that you want, or at least the ones that the question is asking for. If it's saying no bad eggs, well, that's X equals 0. If it's saying 1 bad egg, that's X equals 1. If it's saying more than 1 bad egg, well, that's when you start looking at the discrete methodology. When you start looking at, well, okay, if I want more than 1, that would be 1, 2, oh, sorry, it'd be 2, 3, and 4. For more than 1, you wouldn't be including the 1. That's when you start using complement probabilities to at least minimize the amount of effort that you have to put in. But we'll see that in a few examples. So if you want to find the probability of X equals X, right, that's just finding a specific value. Then you use the Bernoulli sequence as is. Coin is tossed 5 times, so N is 5. Probability of, well, I guess this one you kind of have to guess, well, not guess, but have to know that a coin toss is 50-50. So you put your probability of success as 0.5, your N is 5, and X is 4, because you want to toss 4 heads. Simplify, 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 and you get your answer. If you're using CAS, then binom PDF is the correct syntax for that. That's true whether you're using the Casio or whether you're using the TI Inspire. Both of those are the same. What you'll notice, at least in the TI Inspire, is that it always gives it to you as a decimal. A little bit weird, but I guess it just is what it is. If I show you what that looks like, we would go menu 5, 5. Just going to make sure the camera's facing it properly. I can't click that. Weird. Okay, menu 5, 5. Binomial PDF is all the way down at the bottom, or you can just hit the letter A. Either of those will work. Number of trials we said was 5. Probability of success, 0.5. And we wanted x equals 4. You click that, you get a decimal. At this point, all I recommend is just grabbing a copy of that by hitting enter and highlighting it. Well, highlighting it and then hitting enter. And then enter once more to paste it in, and that'll immediately convert it to the fraction. I used to think you had to go through and go into the number and approximate a fraction. That's not quite necessary anymore. Okay, so if you want to find probability over an interval, that's when you still use Bernoulli sequence, but now you use Bernoulli sequence for a sequence of events. So one of the examples here is a coin toss again, 5 in a row. So it's still going to be 5 and equals 5. Probability of tossing one or fewer heads. One or fewer means one or less, right? And so that means the possibilities there are going to be either tossing one head or no heads. And so you would just individually answer, well, solve each of those probabilities and then do the, where'd that come from? And then you would just do the addition of those two things together. This one in particular wouldn't benefit from using complement probabilities. It's usually when it's a bit crazier. It's actually worth mentioning before I move on that the CAS also has syntax for this. Both TI Inspire and Casio use the binomial CDF. So binomial CDF was a bit off screen at the time. It's down here as B. Binomial CDF, number of trials, same thing. Probability of success, same thing. In this case, we were looking for a lower bound of 0 and an upper bound of 1 because it was 1 or fewer. Lower bound 0, upper bound 1. And then we can just convert that to a fraction if we want to. You can, one of my students used binomial CDF for pretty much everything just because it was easier, right? Only know one function instead of having to use two. The way you use it for everything is that you set, whoops, E55B, you set your lower bound and upper bound to be the same thing. So if you had your 5.5, I think it was x equals 4 last time. If you set them both as the same thing, you actually get the required answer if you had just done the binomial PDF. So we go back and have a look at that example for getting 4 successes. You're still getting that 5/32, which we expected. So just a little tip there. Back to what I was saying before, using complement probabilities. That can be advantageous because it can cut out the number of times you have to solve the Bernoulli sequence. Like this one here, it's saying probability of tossing one or more head. Normally that would mean you have to do x equals 1, x equals 2, 3, 4, 5. But you can use complement probabilities instead. You can just do 1 minus the x equals 0, and that works the exact same way as discrete did, right? 1 to 3, or just doing 1 minus 0. So all you would do is calculate one Bernoulli sequence instead of 4 of them. A lot nicer. This has applications for situations where the n is unknown. So we use that exact same methodology, but with a slightly different or slightly more complicated scenario. Under these circumstances, it's the n that's unknown. So if we look at the information that we're given here, we're told that the probability of winning is 0.25. So that's our P value. We're told to figure out the minimum number of games being n. minimum number that must be played to guarantee the probability of winning at least twice is zero point 0.9. So these tend to be worded in possibly the worst way possible. Um, there's not a whole lot of getting around it. That's just what the wording is. If I had changed the wording, then I wouldn't be preparing you for what was actually the case. So how do you actually digest that? You tend to just sort of yeah. I was trying to think. If you work backwards, it still doesn't really make a whole lot of sense. Just sort of break it down term by term. So minimum number of games, right? When it says what is something, that's the thing that you're trying to solve. So we know at the end of the day that n is the thing that we care about, at least from that statement. Probability of winning at least twice. Okay, well, I know what that looks like. Probability of winning at least twice. That's just x greater than or equal to 2. Okay, well, at least I can write that. Um, Probability of winning at least twice more than zero point 0.9. Well, okay, I can just say that this statement has to be greater than zero point 0.9. Now, I didn't say that immediately. I said that down here at the zero point 0.9, but point being is you have this thing that equals zero point 0.9. So that gives you a statement to work with. Now, the problem with that is that you don't actually know how to solve greater than or equal to 2 if you don't know what n is, right? If you did greater than or equal to 2, it would be x equals 2, x equals 3, x equals 4, but your end point is n. You don't know what that is. And from experience, some of these go all the way up to 15 or 14. So you don't really want to add up 14 of these all together. So the recommendation is, well, if I don't know my upper bound, I do know my lower bound. And so instead, I'm just going to do that. I'm just going to go backwards. Complement to this is going to be x equals 1, x equals 0. And so I'm just going to do 1 minus that. Using my Bernoulli sequence, I could expand each of those out and simplify. So simplifying these factorials down, you don't necessarily have to do that yourself. This is a CAS-enabled thing. And so all you would have to do is go to the CAS, and you would go menu 5, 3, at least on the Casio. I think TI Inspire, oh sorry, on the TI Inspire. On the Casio, it's a bit different. On the Casio, it is under one of the math tabs, I think. Let's see if I can find it without breaking the key. Oh, come on. There we go. Let's see. Can I find it? I only bought this recently. Um, NCR. Now, I think it was in a weird spot. Catalog, maybe? Number. Trying to see it through my camera, so it's a bit harder. There we go, NCR. So you can just literally put in NCR. And if you wanted to simplify NCR and choose 0, then you could just do n comma 0. I'll just use x, but it doesn't actually matter. And that'll actually just give you the answer, right? You don't have to simplify that yourself. If you want to know what n choose 1 is, then you do the exact same thing. NCR x comma 1, and that'll give you what that actually looks like. Oh, it didn't. That's crazy. You guys at the Casio getting shafted. That works on the Cas on the TI Inspire. Watch this. Menu 5, 3, x comma 1, x. So for those of you that have the Casio, you need to brush up on how these actually simplify. So while we're at it, might as well explore what's going on there. Okay. So if you need to simplify these by hand, say we have our n factorial. Let's make that a bit bigger so I don't knock the camera. N factorial, n take 1 factorial, 1 factorial. That's what that was. So how do we handle these? Well, we handle it like we would for any other factorial that we expand. We're just going to expand the numerator and expand the denominator, cancel out the common terms. So for that, it's going to be n, and then n minus 1, and then n minus 2, and so on and so forth. You don't have to write out everything. You'd have to write out enough to where you can see it all. Just going to quickly change my camera so I can see. Yeah, there we go. Um, Same thing below. N minus 1 is where we start. The next one down is n minus 2. The next one down is n minus 3. And that continues forever. You've also got this 1 factorial in there, but 1 factorial is just 1, so you can pretty much just ignore what's going on there. All you do is cancel out all the terms that follow. And what you're left with is just the n giving you n. So that whole mess of factorials is just n. So if we go back to the screen share, or at least if I divert your attention back to the screen share, um, we see that's the case. And everything else is simplified as it needs to. So if we recall what we were actually trying to achieve, it was 1 minus the x equals 0 and the x equals 1. This one's the x equals 0. This one's the x equals 1. Plug them in and then chuck it into a solve. Now, one of the weird things about the CAS, if you put a greater than sign on that, it'll just complain. It'll spit back the same result. So my recommendation is put the equal sign in there instead, because getting an answer is better than not getting an answer at all. So even though you want to put a greater than, because, well, it says more, just put an equal sign. What you'll have to do then is just figure out, do I round up or do I round down? You'll often get two solutions, this sort of thing. The negative one is always the outlier. Can't have a negative number of trials. That wouldn't make any sense. But we also can't have a decimal number of trials either. So what we have to do is, sure, we're going to ignore this one, but we still have to handle the 14 here. In my experience, this always rounds up. If you want to verify whether it rounds up or not, then I recommend just testing. If I plug in n equals 14, do I get a probability that's actually greater than 0.9? So you can go back to your definition of what that probability is and then just test. If I chuck in n equals 14, do I get what I want? And in this case, you would get almost 0.9, but not quite. If you chuck in n is 15, then you get above 0.9, which is what you want. And so in this case, you would give n equals 15 as your answer. That's that's the analytical way of doing this. You can just bash it out, right? You don't actually have to think too hard when it comes to these. These are always CAS questions anyway. And so one of the things one of my students showed me actually, how she does it, is she'll go through and go to the binomial CDF. The number of trials, she'll just guess. We don't know what it is, but we can at least maybe throw a number out there. Let's say it was 10. We knew the probability of success was 0.25. The lower bound is always going to be 2 because it's x greater than or equal to 2. And then all she does is, well, she says upper bound is going to be equal to number of trials because, well, that's what it is. If it's greater than, it always has to cap out at number of trials. And then we just calculate that probability. We see it's 0.75. That is not greater than 0.9. Okay, let's try a bigger number. Chuck it up to 15. Well, actually, that's the answer, so maybe we won't do that. We'll chuck it up to 13. Try a bit higher. All right, we got a bit closer. Let's say we overshot it. We chose 17. Okay, that's greater than 0.9, but did we overshoot it or not? Well, you're just going to walk it back a little bit. Go down to 16. All right, still above. Walk it down to 15. Still above. And then walk it down to 14. That's below. And so you would then just give the 15 because that's the last n value, which is going to give you a probability greater than 0.9. So that's one way of doing it. Don't have to think too hard. Just bash out some n values and see what works. Yeah, personal preference there, really. That's about it for those. I've got a whole bunch of sample problems if you want to have a look at all these. This was just pulled from exam stuff, so it's a bit on the messier side, but it's all the possibilities that I could think of. at least as far as what's been in the exam. That's binomial. That's binomial, that's discrete. There's other stuff as well when it comes to what is it? The statistics, finding mean, finding standard deviations, that sort of thing. Um, but for now, I think we'll cap it since I'm pretty sure no one is going to be joining this class. And I think I said what I want to say um, about the actual issues when it comes to this area of study. Well, hopefully, see you next week.